Gotcha.
This is dark, and it has huge mass, and it's small. That's 3 smoking guns right there.
Right.
Implicating a supermassive black hole.
It might be unsettling to consider space. The perils that lie beyond the great reaches of space can be horrifying. This holds true for the idea of space travel as a whole, but black holes are the one aspect of it all that has always fascinated and alarmed people at the same time. Numerous studies have been conducted on these powerful creatures all throughout the world. Researchers have been attempting to determine the nature of black holes and what is contained within them. But that all changes right now. Recently, Neil deGrasse Tyson made a stunning discovery. Our black hole is smaller than the one at the heart of the Andromeda Galaxy, which is our closest large galaxy. So, we're envious of black holes. I believe that we do. It could simply blow your mind to see what's inside a black hole now that we can finally see it. Come along with us as we explore space and provide an answer to one of the most often asked topics in history. A big explosion produces an amazing phenomena called a black hole, which may be found in space. Since the mass of the black hole is concentrated in such a small area, nothing can escape from it, not even light, due to the strong gravitational field. Anything that enters there will remain there permanently. Star black holes, which may have several times the mass of the Sun, and supermassive black holes, which are found in the cores of galaxies and can have millions or even billions of times the mass of the Sun, are examples of the different sizes of these energy sources. For decades now, scientists have been seeing black holes' impacts indirectly, and hundreds of secrets come to light with each new piece of information that is discovered. They actually have an origin tale, despite the appearance that they are too big and strong to have one. Black holes are made, not only found in space. To be born, they require the remains of enormous stars that have run out of nuclear fuel. These stars explode as a supernova, a dramatic event that signifies the end of their existence. A supernova causes the star's core to collapse due to gravity, while the outer layers are forcefully ejected into space. However, not every collapse is the same. The force of gravity overcomes all other forces, forcing the core to collapse inward, if the mass of the core is many times greater than that of our Sun. A black hole is created when an object with a gravitational field so strong that nothing can escape its grasp collapses to such a small volume due to the extreme compression of material. A black hole's mass determines how big it is. The most well-known kind of black holes are stellar ones, which range in mass from a few times to many tens of times that of the Sun. The singularity, a region of infinite density and space-time curvature, is located in the center of a black hole. The rules of nature break down at this point, as far as current physics allows, and our standard theories are unable to adequately describe what occurs within the singularity. We would have to venture a bit beyond conventional thinking in order to fully comprehend the nature of singularities. A singularity in physics is a location in spacetime where a certain quantity becomes limitless or undefined. These singularities occur in a variety of theoretical scenarios, including the Big Bang singularity the point at which the universe begins to expand and the interiors of black holes. Studying the Big Bang singularity presents a basic problem. The idea states that 13.8 billion years ago, the universe was in a very hot and dense condition. However, the general relativity equations that describe the behavior of gravity degenerate as we travel back in time toward this starting condition. This disintegration suggests that the circumstances surrounding the Big Bang cannot be adequately explained by the state of physics as it exists now. A theory that integrates the ideas of quantum mechanics and general relativity is needed to resolve this problem. You see, singularities are found in the center of black holes. These are areas of enormously bent spacetime where the gravitational attraction becomes endlessly intense. Matter and energy falling into a black hole reach their singularity and become infinitely squeezed, according to general relativity. Even this idea defies everything we now understand about physics. The problem of singularities has spurred researchers to look for a theory of quantum gravity, which would finally bring the ideas of quantum mechanics and general relativity together. The goal of quantum gravity is to offer a theory that can explain how spacetime behaves at both the cosmic and subatomic levels. Such a theory may provide light on the nature of singularities and the true functioning of the cosmos. The theory of loop quantum gravity is one way to tackle the problem of singularities. According to this theory, spacetime is quantized, or made up of discrete, indivisible units, at very tiny scales. These building blocks are frequently called spin networks or loops. The idea of quantization is extended to spacetime itself in loop quantum gravity. This indicates that spacetime is viewed as a collection of distinct pieces rather than as a continuous and endlessly divisible entity. These distinct spacetime units are frequently viewed as linked loops or networks that symbolize the fundamental composition of the cosmos. Black hole and Big Bang singularities might be handled within the context of loop quantum gravity. One of the main conclusions of this theory is that the discrete character of spacetime precludes the development of infinite densities and curvatures, which lead to singularities at very tiny scales. For instance, loop quantum gravity in classical general relativity implies that the spacetime fabric gets smaller as matter collapses into the core of black holes. The stuff can't get to an indefinitely dense singularity because of its size. Rather, in the vicinity of the core, the collapsing matter experiences a quantum bounce, after which it rebounds and starts to expand once again. In this case, a new spacetime area known as a bounce region or a quantum black hole is created within the black hole. The singularity problem can be solved because the bounce area takes the place of the classical singularity. Similarly, loop quantum gravity suggests that the cosmos was not initially defined by an indefinitely dense solitary point in the case of the Big Bang singularity. Rather, the cosmos arose from an earlier quantum gravitational phase in which singularities are prevented by the structure of spacetime. This circumvents the singularities seen in traditional models and offers a fresh viewpoint on the universe's creation and development. The aim to harmonize the fundamentals of quantum physics with the way that physics treats singularities in its classical form motivates the hunt for a unifying theory. Closing this gap could lead to fresh perspectives and solutions to the problems that singularities present. However, there are so many different kinds of black holes that even this suggested remedy falls short. The most prevalent kind of black holes in the universe are stellar ones. They are created near the conclusion of a large star's existence by gravitational collapse, as we briefly discussed previously in this video. The outward pressure created by nuclear reactions can no longer resist the inward pull of gravity once a large star has used up all of its nuclear fuel. The star collapses under the weight of its own gravity when the gravitational pull grows stronger. A stellar black hole is formed as a result of this collapse. The star compresses exceedingly tightly during its collapse, cramming a large mass into a tiny space. Because of this, the mass of stellar black holes usually ranges from a few times to around 20 times that of the Sun. Their sizes are very modest, despite their heft. Their very thick nature is further demonstrated by the fact that their diameter is barely a few kilometers. An event horizon forms as a result of a stellar black hole's extreme density. Beyond this point, nothing can escape, not even light. This event horizon indicates the point of no return, where an item or piece of information that passes through the black hole's gravitational force is permanently imprisoned inside the hole. Next, there are black holes with intermediate masses. Although further study is needed to determine the exact mass range of intermediate mass black holes, it is generally accepted that their masses vary from hundreds to tens of thousands of times that of the Sun. Comparing them to a stellar black hole, they would be far denser. Although the generation mechanics of intermediate mass black holes remain mostly unclear, two main hypotheses are now under investigation. One explanation is that they originate from the merger of many stellar mass black holes in areas of space where there is a high density of massive stars, such galactic centers or globular clusters. Binary systems can arise as a result of interactions between stars. Gravitational interactions can force these binary systems to combine over time, eventually leading to the formation of an intermediate mass black hole. According to the second creation model, huge gas clouds in the early cosmos directly collapsed to generate intermediate mass black holes. These gas clouds, which are concentrated areas of primordial matter, have the potential to rapidly collapse due to gravity, becoming an intermediate mass black hole rather than a star. Stellar black holes are far more abundant today because of a mechanism that may have been more common during the early phases of galaxy formation when gas concentrations were higher. Due to their limited quantity and enigmatic character, one of the biggest problems with intermediate mass black holes is that they are very difficult to discover. However, indirect methods, such examining the motions of stars and gas close to these possible black holes, have allowed for the detection of their presence. The existence of intermediate mass black holes in galactic nuclei has also been suggested by recent findings, suggesting that they may not be as rare as previously believed. With masses ranging from millions to billions of times that of the Sun, supermassive black holes are the big dogs of the black hole family. These enormous creatures are found at the centers of most galaxies, including the Milky Way. They have a strong gravitational pull on the objects in their galaxy and a strong influence on the galaxy's development. Supermassive black hole generation is still an active field of study with many unanswered questions. Even yet, several hypotheses have been put forth to account for their genesis. According to a well-known theory, supermassive black holes form through a process known as accretion from smaller black holes. This theory states that stuff, including gas, dust, and stars, builds up around black holes to form accretion disks, which are spinning disks. Material from this disk is drawn inside by the black hole's strong gravitational attraction, spiraling inward until finally merging with it. This constant matter accretion over extended periods of time enables the black hole to reach supermassive proportions. Massive quantities of gravitational potential energy are released as matter falls into the black hole during the accretion phase. Some of the universe's brightest and most potent occurrences are propelled by this unleashed energy. Charged black holes, on the other hand, are a unique kind of black hole distinguished by the existence of an electric charge. They exist apart from all of that. Reisner-Nordström M and Kerr-Newman black holes are the two primary varieties of charged black holes. Different characteristics are displayed by each kind, which arise from the interaction between the black hole's charge and other parameters like spin. Reisner-Nordström M black holes do not rotate, yet they are charged. The Reisner-Nordström M solution within the context of general relativity describes them. These black holes' charge has an impact on how their gravitational field behaves. Reisner-Nordström black holes, however, resemble uncharged black holes in terms of their general structure. A Reisner-Nordström black hole has an event horizon, however the size of the horizon is dependent on the black hole's mass and electric charge. Kerr-Newman black holes, on the other hand, rotate and are charged. In general relativity, they are characterized by the Kerr-Newman solution. Unique phenomena related to these black holes are introduced by the combination of electric charge and spin. A prominent phenomenon known as frame dragging arises from the spinning black holes tugging and twisting of the surrounding spacetime. The Cauchy horizon is an inner area of Kerr-Newman black holes that exists in addition to the event horizon. This is the inside barrier of the black hole dividing the region outside from the singularity's location. The spin and charge of the black hole affect the Cauchy horizon's characteristics, which add to the complex dynamics in the vicinity of the black hole's core. The effects of spin and charge of the black hole become prominent near the Cauchy horizon. The Cauchy horizon is linked to an issue with a general relativity theory called the cosmic censorship hypothesis. According to this specific theory, singularities within black holes are always concealed by event horizons, meaning that any impact they may have on the outside world is always out of view. The veracity of this idea is closely linked to the behavior of the Cauchy horizon. The Cauchy horizon would stay buried within the black hole and its complex dynamics would not be seen from the outside if the cosmic censorship hypothesis is correct. It would be an understatement to suggest that it is therefore crucial. But they also have a different aspect to them. In the field of astrophysics, undiscovered and speculative black holes provide intriguing research opportunities. Even though the black hole kinds discussed previously are well understood, black hole research still has uncharted territory. The presence of primordial black holes is one field that is still being studied. These are speculative black holes that could have developed soon after the Big Bang in the early cosmos. The genesis methods of primordial black holes are different from those of stellar black holes, and they would have arisen from areas of high-density fluctuations. They differ greatly from other types of black holes we often meet in that they might have a wide range of masses, including small black holes known as micro-black holes. Investigating revolving black holes with enormous angular momentum is an additional intriguing direction. These hypothetical black holes, sometimes referred to as extremo black holes, spin at the fastest speeds conceivable. They stretch the boundaries of what we currently know about black hole physics, which makes them quite interesting. However, the idea of dark matter is one that is always brought up in relation to black holes, regardless of the kind of black hole being discussed. Dark matter is a special kind of stuff that contributes significantly to the mass of the cosmos, substantially more than the amount of directly observable conventional matter. It is difficult to detect and investigate, which is why it is dubbed dark, because it doesn't interact with light or other electromagnetic waves. Actually, the large-scale structure of the universe and visible matter are subject to its gravitational pull, which allows for the detection of its presence. Though its precise nature is still unclear, a number of hypotheses indicate that dark matter was essential to the development and evolution of galaxies, including the creation of black holes. According to one idea, dark matter serves as the framework for the assembly of galaxies. Massive structures like galaxies are formed when ordinary stuff, like as gas and dust, is drawn together by its gravitational attraction. These formations can potentially give birth to the circumstances required for black hole development as they develop. By exerting a gravitational pull on matter, dark matter is essential in determining how matter is distributed across the universe and in establishing the ideal conditions for black hole creation. Another idea is that primordial black holes make up dark matter itself. The development of further stars and galaxies surrounding these primordial black holes might have been impacted by their gravitational interactions, if dark matter is made up of them. Though dark matter is abundant everywhere, it is unlikely to directly generate black holes, which is a crucial point to remember. It is believed that normal stuff, such huge stars, collapses to generate black holes as we know them today. On the other hand, charged and spinning black holes appear to be related to dark matter. Black holes might live longer and exist for extended periods of time if they have spin or electric charge. This may enable them to serve as a reliable source or reservoir for dark matter particles, which may help to clarify the characteristics of dark matter and its place in the universe's creation and development. However, the majority of the data comes from the most thorough research of known black holes, which is made feasible by our advanced technological capabilities despite the challenge. 4 separate telescopes, each with a main mirror of 8.2 meters in diameter, make up the Very Large Telescope, VLT, at the Paranal Observatory in Chile. Numerous cutting-edge equipment, like the multi-unit spectroscopic explorer and the spectrograph for integral field observations in the near-infrared, are installed aboard the VLT to assist examine black holes at various wavelengths in greater detail. These tools offer spectroscopic and high-resolution imaging capabilities for researching the behavior, composition, and dynamics of black holes. The Event Horizon Telescope, EHT, is the next in line. This is essentially a virtual Earth-sized telescope made possible by a worldwide network of radio telescopes that are synchronized to watch concurrently. By identifying the signals from many telescopes throughout the globe, the EHT is able to get a resolution never before seen and provide finely detailed photographs of black holes. In 2019, the partnership achieved a significant milestone by taking the first direct picture of the event horizon of a black hole, namely the supermassive black hole situated at the heart of the galaxy M87. This groundbreaking discovery revealed the existence of black holes through visual proof and revealed details about their composition and surroundings. But this is only the beginning. The gravity instrument is another. This is an interferometric device that was put at Chile's VLT. It creates an interferometer with exceptionally high angular resolution by combining the light obtained from 4 VLT telescopes. Gravity's main purpose is to examine the region immediately around black holes, including their jets, accretion disks, and gravitational interactions with nearby stars. It does this task flawlessly. However, it receives some assistance from the Extremely Large Telescope, ELT. The biggest optical and infrared telescope in the world is the ELT. When finished, It will have a 39-meter diameter main mirror and incredibly strong light collecting capacity. By compensating for atmospheric imperfections, the ELT's sophisticated adaptive optics technologies will produce remarkably clear images. The study of black holes and other celestial phenomena will be greatly aided by this state-of-the-art telescope. With it, we are able to examine in unprecedented precision the processes of black hole accretion, the development of supermassive black holes, and the relationship between black holes and their host galaxies. Since dark matter has a gravitational pull on star motion inside galaxies, astronomers may also identify the presence of dark matter by tracking star orbits around black holes. Astronomers examine how the gravitational attraction of visible objects, such stars and gas clouds, impacts the stellar orbits while observing the motion of stars around a black hole. The existence of extra mass, which is attributed to dark matter, is suggested if the observed motion cannot be explained by the visible matter alone. Dark matter is a kind of stuff that is elusive and invisible to light and other electromagnetic waves. Its gravitational pull on nearby objects is the sole way to determine its existence. If dark matter is present, its gravitational pull affects the orbits of stars around a central black hole. However, it's the point at which researchers must go above and conduct study that genuinely has an impact. Examining binary systems in which a black hole and companion star are engaged in a gravitational dance is one method. Astronomers can determine the companion star's decay rate by tracking its orbital motion. If the decay is occurring at a slower rate than expected by established physical principles, this might indicate that dark matter is responsible for the extra mass impacting the orbit. This effect has been seen in several binary systems, which lends credence to the theory that there is a significant quantity of dark matter surrounding black holes. Analyzing the orbital periods of stars close to black holes is another technique. The duration of a star's orbit around a black hole is measured by astronomers, who then compare the results to theoretical estimates. The presence of extra mass from dark matter encircling the black hole may be indicated if the measured orbital duration is noticeably shorter than predicted. Another idea is that dark matter is extremely concentrated in the vicinity of black holes. In order to estimate the characteristics of dark matter indirectly, astronomers study how stars behave near black holes. You can't accomplish anything when one of the primary study components is obscured. You have to rely on everything surrounding it. The interstellar stuff becomes caught in the gravitational pull of the black hole as it passes over the event horizon. The enormous gravitational pull that the black hole exerts prevents the stuff from escaping. The stuff creates its own accretion disk as it spirals inward into the black hole. The falling matter's angular momentum causes the accretion disk, which is what keeps it orbiting the black hole until it is finally devoured. It is caught in the gravitational pull of the black hole. The black hole's tremendous gravitational pull prevents the stuff from leaving. However, many mysteries remain regarding the interior dynamics of a black hole. Renowned astronomer Neil deGrasse Tyson has shed light on theories about wormholes and black holes, specifically on the potential for these celestial objects to act as gateways to other realities. In a 2015 YouTube video, he delves into the mechanics underlying these fascinating events. According to Tyson, wormholes are theoretical formations that would be able to link two far-off locations in spacetime, therefore building a bridge or a shortcut across several universe regions. Even while wormholes are still theoretical and hypothetical, their potential to allow for faster-than-light travel and easier interstellar travel has drawn the interest of both scientists and science fiction fans. Tyson discusses the idea that black holes might be gateways to alternate worlds. According to him, black holes are areas of space with extremely intense gravitational pulls. Black holes may act as portals or gates to other worlds in some theoretical scenarios. These ideas suggest that the intense gravitational pull of black holes might form a conduit or link to other regions of the universe. It would completely upend our understanding if wormholes were found to exist on the opposite side of black holes. The presence of a bridge or passageway across far-off areas of the cosmos would be suggested by the discovery of a wormhole within a black hole. This would go against everything we now know about space and open the door to the possibility of accessing other galaxies or universes, as well as interstellar travel. Furthermore, Black holes are already strong things. An additional level of complexity would arise from the existence of a wormhole inside them. It would suggest that in addition to having extremely strong gravitational fields, black holes are also capable of supporting and enabling wormholes. This may offer fresh perspectives on the basic principles of space-time dynamics and the physics regulating black holes. That's not all, though. The idea of a multiverse, in which several worlds coexist, would be supported if the opposite end of a black hole's wormhole connected to another reality. That's actually fantastic since pop culture has been focusing a lot on it these past several years. At least then we would be aware of everything should it occur. Examining these links may reveal distinct physical rules and constants and provide insight into the features and attributes of parallel universes. Furthermore, the existence of navigable wormholes inside black holes may contradict our conceptions of causality and time. It opens up the ability of going back in time or forward in space, making it possible to take trips into the past or future. Neil is not alone, though, in putting up the idea of time travel. Many hypotheses propose that black holes might function as natural time machines. The phenomena of time dilation, in which the strong gravitational attraction of a black hole alters the passage of time, is one fascinating feature of this situation. Time may be severely warped close to a black hole, which causes notable variations in how quickly it passes relative to observers farther away. It has been proposed, for example, that a year in close proximity to a black hole may be compared to decades or even centuries on Earth. The potential of time travel with black holes is sparked by this time dilation effect. It poses the possibility that passing through a black hole's strong gravitational field may move a person into another time frame. Black holes induce a severe curvature of spacetime, which gives rise to intriguing theoretical situations. It is conceivable that in the vicinity of a black hole, space and time may be so drastically bent that they could fold back on themselves to create what is known as a closed time-like curve. According to this theory, there may be a time loop in which it is possible to travel down a road that takes one back in time. Given that nobody is quite sure where to start or stop, this kind of time travel may be among the riskiest. However, it's also crucial to remember that, despite the fact that it sounds really fascinating, going beyond the event horizon euro, the point at which a black hole is no longer accessibly a euro, has serious repercussions. It is extremely difficult to escape the black hole's grasp because of the gravitational pull that is created at the event horizon, which causes an increasingly steep gravitational potential. The enormous pressures involved are thought to cause strong gravitational tidal forces to rip apart anything that approaches too closely. Strong enough to accomplish it are even the black holes found within our galaxy. Which gets us to the one issue that people tend to ask all the time: what does it all imply for Earth? Could it really suddenly be engulfed whole by a black hole? The solution to this one is a little more nuanced, though. Extremely dense objects with a powerful gravitational attraction are known as black holes. Although our Milky Way galaxy is home to a few supermassive black holes, the likelihood of Earth being engulfed by one directly is extremely remote, at least not at this time. Any considerable shift in Earth's gravitational force would actually require the collapse of our Sun into a black hole of the same mass, a situation that would not be dangerous to Earth. V616 Monocerotis, the nearest known black hole to Earth, is still too far away to have any effect on humans. It is around 6.6 times as big as our Sun, and we would have to approach it to within about 800,000 kilometers for Earth to be ripped apart by its gravitational pull. But since such an occurrence is extremely unusual to happen within our lifetimes, this one is definitely one for the record books. A further off worry is the possibility of our galaxy colliding with another. In this case, Earth may be propelled by gravitational interactions toward the galactic center, home of a supermassive black hole. Don't panic, though. It's estimated that this impact will occur around 4 billion years from now, giving plenty of time for natural processes to determine our planet's fate and evolution. The side of Earth nearest to a black hole would feel a far stronger gravitational pull than the distant side in the unlikely event that Earth did reach the black hole's event horizon. Our world would be completely destroyed due to the tidal forces that will ensue. But initially, at least for a short while, the experience within the black hole's event horizon would seem unchanged. It is important to realize that there is very little chance that Earth will come into direct contact with a black hole. We are not now in danger from the black hole in our galaxy, which already has a mass millions of times greater than the Sun. Furthermore, stars further away from the black hole are comparatively secure from its gravitational attraction, whereas ones closer to the hole have probably already been devoured. So perhaps Earth is secure for the time being. Did you enjoy this video? Please like and comment below. Turn on the notification bell to get notifications for videos like this.